So I'd like to do another example of magnetic force between wires. In this case, we're taking a slightly different example where we have a loop, a rectangular loop, a width W, height H. This is in the plane, so is it really a height? Whatever, it doesn't matter. WH, we could have called it L, WL. Anyway, those are the two dimensions, and we have a long straight wire, I1, and the coil, the loop, the single loop, we'll just have it a single loop. The loop is carrying current I2. And by the way, let's just make sure we understand physically how we make a loop carry current. A single loop that's not attached to anything can't really carry current because there is no power supply to create that current. But actually, if it was a superconductor that didn't have resistance, what you could do is you could put current in, take away the power supply, and if it was still superconducting, that current would just go around and around and around. That's an unusual situation. In reality, what we are approximating with a single loop is a coil, right? So that what we really have, or maybe a coil, a single loop from a coil, right? So a single loop from a coil, and we're just looking at one of those loops. Or it could just be something that looks like this, right? Those are the wires, and we're just interested in the loop, okay? So there is really no such thing except for a very special superconducting loop as that. By itself, it does have wires, but that's the same thing that we're doing with this, right? We're saying here there's also a power supply that has got to give us this current. We're just not looking at the power supplies. We're not looking where the currents are coming from. So these are valid problems. They're just approximations without taking into account the fact that we actually have power supplies. Okay, do this problem. What is the magnetic force on the loop due to long straight wire? We could give numbers, but it's just a plug-in in the end. So we're just going to say what is given is I1, I2, W, and H. And we want to find the magnetic force on the loop. And in this case, it is the magnetic force, not the magnetic force per unit length. Because the magnetic force on, let's just look at this at the four sides of the loop, right? The magnetic force on that side of the loop is going to be, I didn't give you a distance. Let's just say that the close side of the loop is D away from the wire. So that is another given I have to give you. Whoops. I have to give you D. Okay, so the givens are D, W, H, I1, and I2. So you got to write everything in terms of the given quantities and any constants. Okay, so once again, the side closest to the current and the side farthest side closest to the current and side farthest away from the current are going to feel different forces because they're different distances away, and magnetic field gets smaller as we get farther away. Now what? So we got, but they're still parallel wires, so we can figure those out. So we're going to call this the force on the side closest. We'll just call that force 1. We'll call this the side farthest away force 2, and let's talk about the force on the right side, force 3, and the force on the left side, force 4. So let's just calculate those four forces separately. So let's just simplify our lives to start with and say that the force on this side of the loop is harder to calculate than the force on 1. Right, because force on 1 is two parallel wires, the magnetic field on 1 is constant everywhere, whereas the magnetic field on what we call side 3, it varies. And so in order to find the force on 3, we would have to do, once again, we could actually do the integral. We could find the force on side 3. Side 3 is the right side. Okay, don't be confused. It's got a current I2 in it. We could find that, but it's an integral, right? So we're using I dl cross B, and then we have to add it up as B changes. But the cross product, the magnetic field is perpendicular to side 3 everywhere. So the cross product goes away and it just turns into I dlB, and we can figure out the direction in a second. So let's go ahead and do that integral. not 100% sure. It wasn't recording. But let me just restate real quick. I'm not sure what I stated. I'm sorry if this is a repeat. But we've got the green R pointing to DL. DL is along the same direction as R, so DL is equal to DR. So I have made that substitution. DL is equal to DR. B is the magnetic field of wire 1, so I've made that substitution right there. And R goes from the closest distance of side 3 is D, so I'm looking at the limits of the integration, and the farthest is D plus H, so that's the limits of integration. Pull the constants out of the integral, and we can do this integral. And you might remember from before, you just need to really know this, or I'm not sure I would ever ask you to reproduce it, but you should probably know that the integral of 1 over r is the natural log of r, and then when we plug in our limits, we're going to get natural log of d plus h. Okay, so that is the actual force, not force per unit length, but force on on the right side. I think the part that I said when I wasn't recording is that, remember that the force, the original equation, is a cross product, right? So let me just write that over here, right? dF is equal to I dl cross B. If everything's constant, that's just F equals IL cross B. But if something varies, we have to do the integral. And that cross product gives us a sine theta, and theta is 90 degrees, so that cross product, just sine of 90 degrees is 1. The cross product goes away, and I just wanted to make sure that you could see that for yourself. So that's why we just have IDLB. And the direction is given by the right-hand rule. DL is down the page, B is into the page, so you put your fingers down the page, you rotate them into the page, and the force on the right-hand side is to the right. But that was completely unnecessary in order to answer this question, because, look at the force on the left. The force on the left is going to be the exact same thing, but it's going to point in the other direction. So F4 is going to point to the left, and F3 is going to point to the right. So those two forces are equal and opposite, and so those two forces cancel. So you didn't actually have to do the integral in order to answer this question. So the force on the right is equal and opposite to the force on the left because it's completely symmetrical. Whereas the force on the top, 1 and 2, are not equal and opposite because they're different distances away from the wire. So let me come back to this problem clean. We can either calculate or you can argue that the force on the right is equal and opposite to the force on the left. I just want to see, I called the top one F1, F2, F3. Whoops, F1, F2, okay. So there is a magnetic force on this one, which is F1, and a magnetic force on this one, which is F2. And then the right and the left cancel. So the net force is just going to be F1 plus F2. So let's go ahead and figure out the force F1, right? F1 is, in magnitude, it's I1, which has a length of W, and it's in a magnetic field of B1. Gosh, I messed that up, didn't I? The force of side 1, it's the numbering that's I should have called them top. I should have called this top, bottom, left, right. That would have been a lot less confusing. I apologize. So let's just go ahead and change that to F top. F top is equal to I in the top times W times the magnetic field, which is the magnetic field due to the current long straight wire B1, times the sine of the angle between what? Between this length and the magnetic field due to I1, right? And the magnetic field due to I1, by the right-hand rule, is into the page. B1 is into the page. Okay, so what's the angle between L and B1, or the length of that wire, or the current direction of that wire, and B1? The angle is 90 degrees. So the magnitude of this force, the force on the top, is equal to I on the top, which is I2, times the length of the top, W, times B1, which is mu naught I1 over 2 pi D. Again, I didn't write the D here, but I said that this was D. So that's the force on the top wire. What is the direction of the force on the top wire? The direction of the force on the top wire is, again, L cross B. L is to the right, B is into the page. And so that is, it's attractive because those two currents are in the same direction. It's towards I1. Okay, let's do F bottom. Now you should be able to do F bottom pretty easily. F bottom is the force on the bottom is the current on the bottom, which is I2, times the length of the bottom, which is W, times the magnetic field at the bottom. This is where you got to be careful. The magnetic field at the bottom, due to I1, is mu naught I1 over 2 pi, and the distance is D plus H. Right, the distance from I1 to the bottom is D plus H. And what is the direction of that force? Well, that force is they're in the opposite direction, so it's a repulsive force. Hold on. Sorry, you heard that. My phone rang. Okay, so the bottom force, they're in opposite directions. The currents are in opposite directions, or you could do the right-hand rule and figure it out. It's a repulsive force. And which one's bigger? Which force is bigger? Well, hopefully you can see that the force on the top, the closer wire, is bigger than the force on the bottom. So in order to figure out the net force, we can just do F top minus F bottom. F net is F top minus F bottom, because they're in opposite directions, right? It's plus a negative F bottom, because they're in opposite directions. And then, so that's going to be the net force, is going to be that. And that net force, because the top, because this one is bigger, the net force is going to be towards. So the net force is just adding up those two vectors, F top and F bottom. These are vectors. Adding up those two vectors, recognizing they're in opposite directions, so you got the minus sign between them. And the net force is towards. So this loop is going to be attracted to the current carrying wire I1.